There we are. Okay. How do I look? Anyway, I also like the way I came into Microsoft. Before I actually joined Microsoft 7 years ago, I was maintaining the Postgres.NET driver, and I also came to maintain the .NET ES Core provider for Postgres. So everything having to do with Postgres and .NET is kind of like my world as well. I traditionally love perf, a bit like Adam, but perf in databases is usually a bit less about profiling and reducing allocations and a bit more, for example, in EF, it really means the really impactful thing is more generating slightly better SQL so that the database can actually plan better for the query, and much less that's impactful. That's like orders of magnitude rather than a 3% runtime sort of thing. So it's a very different sort of perf, although I love any sort of perf, and I came here from Berlin today. So a few quick words about what this talk is about. So this talk is actually useless. It's a useless talk. What that means is this is not going to talk about any APIs like Adam, for example, was talking about. It's not introducing something cool that you will be able to use in the next release. It's not discussing anything actually that you can actually use directly. We are just going to dive deep into the internals of EF Core. Of course, it's not completely useless. I'm a big believer in understanding what's happening under your feet, right? Like you should not just be programming with the APIs. You should kind of understand how these things do their job so that you can use them more effectively. And it's just very interesting as well, which is why I love, this is my favorite kind of talk. I'm going to kind of, like the talk is arranged around perf and caching inside EF Core, but I kind of use it more as an excuse to explore how EF Core is built. So caching and perf is very cool, but the main point here is to give you an idea of how the query pipeline inside the EF Core works. So how EF Core basically goes all the way from a LINQ expression tree to SQL at the end of the pipeline. That's kind of like the idea. And we'll go through many, many tricky cases. Like you maybe if you've never thought about it. By the way, how many people here use EF Core? Sorry, I should have maybe started with this. Wow, that's a lot. Probably most of the people. That's very cool. You've probably not thought too much about how EF Core does its job. It's actually very, very complicated, as you'll see in this talk. There's many, many cases where it looks very trivial to just go from, LINQ to SQL. It's not very simple, like at the actual, when you look at it. And the one last thing that I really want to kind of drive home is why EF Core is not an ORM like a standard ORM that you're used to. In fact, EF Core does a lot more work. It's like an order of magnitude more complicated than almost any other ORM that you're going to be using in a different language. And I want kind of you to gain an appreciation of why that is. So let's start diving in. So just to set the stage and to remind people, everybody here almost is an EF Core user. That's very cool. We have a common ground, but I want to go through like one slide on the basics. So C# is kind of special. When we want to use an EF Core query, we're just using C# code in order to express it. That's actually quite unique, right? We're not writing SQL, we're not doing some magic string, and we're not using a special API. We're using the exact same LINQ API that we use to query over objects in memory, right? So this where looks like the same where that you use. It's after context block, so it's an EF thing. It's anchored on an EF thing called a DB set, but it looks like this where looks completely like any other LINQ expression that you're using in your day-to-day non-EF C# programming. And this is just C# code. If you get something wrong here, it doesn't compile exactly in the same way that normal code doesn't compile. And at the same time, when you do this thing, this code does not get executed in .NET in any way. I hope this is clear. It's actually very, very weird when you kind of think about it. What happens, in fact, is that this where here and the lambda inside get handed to EF Core as an expression tree. So we get a representation of the code basically that the user expressed in their source code file, and it's up to us to take this as an abstract syntax tree. Maybe you know this, you've gone through this in university, and to make something out of it, translate it into SQL, get the results, and all of that kind of stuff, right? It's kind of magical. This feature of the language that allows this, the technical name that is sometimes used for this is a quotation. So a quotation is part of your source code or a construct in the language that isn't evaluated or executed. Instead, it's built as an expression tree representation and handed off to some component. C# has limited support for quotations, which is what allows EF Core to even exist. If we didn't have quotations as a C# feature, EF Core could not exist as it exists today. That's very important. And most other languages actually don't have quotations, which is why if you want to do EF Core in Java, you literally cannot. You cannot do a thing in Java where you just write Java code, and magically somehow that takes is taken by somebody and translated to SQL. ORMs look different, and that's already starting to make you understand the thing that I was trying to say before. Just to give an example, if you look at another ORM, this is what Juke looks like, a very, very nice, very popular ORM in Java land. So what you have here is something like select, from, where, and order by. That's a DSL. It's a domain-specific language, right? Where you're using Java code. So this is already, by the way, great progress from the old days where you would put, of course, you can always put SQL in a string, right? And then you have magic strings, and if you get something wrong, then it fails at runtime, and refactoring is impossible because it's all just a bunch of strings, right? So the second phase was kind of like still use strings, but we have a special language which is an abstraction over SQL, like Hibernate QL. There's all kinds of generations of ORMs. This is very cool because it's very strongly typed, right? I can't, like the book and the book title and all of these things, if I get them wrong, then I get a compilation error, like in LINQ, which is very cool. But crucially, what I'm doing here is I'm actually expressing SQL. So I'm writing SQL, I'm just not writing it as a string. That's very important. The concepts that I have here are concepts like from and select and where. And these are not things that exist in C# natively. These are completely different concepts. If you want to do a join, if you want to do like a join of two tables, you have a join operator here. If you want to do a join in here in EF Core, you usually don't do a join. You have a join operator in LINQ, but that's not usually how you do it. If you want to check a property in here, then you just dot into it like you would in any normal C# kind of context, right? Completely different, and we have to kind of bridge over that gap. So that's already like a very, very important thing to keep in mind, why EF Core is so different from any other ORM. It's because it's a LINQ provider. That means many, many things. So let's now dive in. That was a sort of a little introductory thing. Let's start diving into how things look like on the inside of this thing. So we have the same expression that you saw here. We're going to keep this and we're going to develop it slowly, or actually quickly. So basically what you have here is a very high level kind of diagram of EF Core's query pipeline. By the way, that's just one part of EF Core. EF Core doesn't do just queries. It has many things. It has migrations. It has an update pipeline for savings. It has a change tracking component. It has a scaffolding mechanism. There's many, many things in there. Each one of them is a big project that can be maintained and all of that kind of thing. We're going to be concentrating on the query pipeline, which frankly is by far the most complicated part of EF. Really, this is where a ton of the complexity is. So what EF Core does, at the left side, we have our input, which is some sort of representation of this thing. It's a LINQ expression tree or a LINQ query tree. That's the input. We get it from, we don't know where it comes from. The compiler basically does it for us, and so on and so forth. Then there is a phase that is very long that we call compilation inside. And compilation is the act of taking the input LINQ expression tree, which it's a representation of the C# code. And at the very end of it, we get two things. We get the SQL. That's the normal thing that everybody expects an ORM to do. We also do another thing that's very important. Nobody thinks about this. We also generate a piece of code that knows how to read the results from this SQL query back and materialize them as objects in .NET, right? That's like a task that every ORM does. If you just send the SQL to the database, you get a table of the results, like a relational table. That's not yet like what the user wants, right? The user doesn't want to go and figure out how to read those rows and columns. They want us to hydrate or materialize or whatever those results as their objects, right? In this case, as a bunch of blogs instances. So we generate this piece of code which does that as well. These are the two outputs from our compilation process. We call this compilation because if you actually look into this, you will see something that really, really resembles what happens in a real compiler. Like there is a little bit, sometimes I talk to some of the people working on Roslyn, and we have some of the same problems and techniques. We use expression visitors to take an expression tree and transform it in various ways. Like it's working on the query pipeline in EF is sort of kind of weirdly being a bit of a compiler engineer. It's very weird. Except that the compiler people compile C# down to IL, which the JIT will then compile down to machine language. We compile C# we compile laterally. Instead of going down like a compiler, we kind of translate laterally to SQL, which is another high-level language, which is why I think of EF Core as a transpiler. Right? Instead of compiling down to something low level, we actually translate from one high-level language to another high-level language. That's basically what EF Core is. But that's actually not what this talk is about. That's another future talk. Who knows when I'm going to be doing that. So this is going to remain a black box in this kind of talk. And we're going to be thinking about how we make this kind of perform in this whole thing around this compilation process. This really does take a long time. That's why I put the word long here. So you're kind of seeing where this goes. We're going to build a whole system of caching around it and evolve it. So what does the actual input look like? I do want to make sure everybody is kind of comfortable with the idea of abstract syntax trees, or what does a representation of a language construct look like in C#. So LINQ expression trees are a weird part of .NET. It's like an official API. You can go into the system LINQ expressions namespace, and you'll find all kinds of weird things, which I deal with in my day-to-day, but nobody else does. Like almost nobody ever touches these things, although you can. What you see here, I've taken this query that we're looking at, and this is basically how it gets handed to EF Core. So you've got something called a method call expression, which represents this where. Okay, it has one parameter. So this is an extension method. It doesn't have any instance because it's just an extension method, a static extension method. It has the first parameter, which represents the DB set. That's the less interesting part. And then it has another, I've glossed over some details here. There's a lambda, there's a quote, but the important thing is the body of the lambda, which is a binary expression. That's the greater than. It's a binary expression with an enum that says, I am a greater than node in the language, right? This is a description of the thing. On the left side of it is the member expression, which represents the dot that you see here. It has the name ID right on it, and then it has the expression as a subnode, parameter expression in this case, which represents the B. Expression trees are highly recursive, so instead of having a parameter expression, you could have a whole tree that reaches all the way down to the floor with arbitrary function invocations and another thing and this and that and so on. It's very recursive and very like open, and it's very cool to work with, but also kind of a mind bend sort of thing. On the right-hand side of the greater than, we have something called a constant expression because it's a literal that appears in the source code. So this is the input that you get to EF Core, and the job is to somehow take this and make it into SQL at the end. Right. First, we said that the compilation process is a little bit slow. So how do you fix basically any performance problem? Either you call Adam Sitnik to optimize it away and introduce spans and all that kind of stuff, or if you're a bit weaker, then you basically just introduce a level of caching, right? Like I'm kind of making jokes, but in many, many, many cases, the way to solve a performance problem is to not do the same work twice. So what we're going to be doing here, we're introducing a mechanism where the first time we see a query in EF Core, you start up your application, we see the query for the first time, we're going to have to compile it. At some point, it does have to happen, this heavy process. But the second time that we see this query, we're going to jump over the entire compilation process. That's our goal here. And that means that we pay some startup price or warm-up time when the application first starts, but pretty soon the application will reach a steady state and all of the queries are cached and we no longer need to compile anything anymore. That's kind of like how EF Core handles the performance problem of compilation. Unless the queries are dynamic. Very good point. So some people, like this sort of mode that I've been showing here, where the query is written like this, is great. But some people will go into this LINQ expression tree API and actually construct nodes dynamically, for example. They might add more conditions here based on some user input that comes in, and that can be absolutely anything. Usually that's still, it's very rare to see that openly dynamic query scenarios, like completely open, where every query looks completely structurally different. We will see just in 2 seconds how some form of dynamicity actually can be taken care of, not really be dynamic. But you're absolutely right in theory, yes. Yes, the cache has a finite size. Every cache in the world must always have we don't want it to grow infinitely, obviously, and fill in the memory. So there's a finite size. You can even configure it, although nobody cares and it doesn't matter so much, but you can if you really want to go into it. There's an LRU sort of cache where anyway, that's like too much in the details, but very good comment, absolutely. And yeah, please feel free to kind of interrupt in the middle. I'm completely fine with it. Be at ease. So the thing with caching, when you do a caching system, you always have a cache key. So what's the cache key in our current situation here? It's a weird cache key, right? In our case here, the cache key is in fact the entire expression tree. The moment that anything in this expression tree changes, like this node at the very bottom here, instead of being a B, it's something else, then we no longer can use the same SQL anymore, right? Because it will obviously result in different SQL, right? So the entire expression tree has to become the cache key. That's a bit that's a bit atypical. Usually we like our cache keys to be like an int or a string. These are very small, relatively speaking, very small and very efficient sort of cache keys. You calculate the hash code once, boom, you're done. You have a dictionary, you're finished, right? Yeah. Yeah. So it is not the same. Could be. Because it doesn't really matter. Nobody actually writes the same query, but with two different like identifiers. This is not a thing that we see. We could, you know what? I'm not even sure if we didn't implement this very specific optimization for the caching, but it's not something that we see in queries. Either the query is different structurally, or it is not different structurally. That's kind of like the way, and when I mean different structurally, I mean like the nodes are actually different. And not just because what you're saying here, this B, means that somebody actually wrote the exact same query here, but just replaced the B with a C. It absolutely can happen, right? And again, that actually, that's a good question, and I'm not 100% sure that I can answer no. I'm only 99% sure. You know what? That's a very good thing for us to check and to maybe look at. That's I like that question. That's a very good question. And not just the hash code, you also have to compare for equality because two different things might have the same hash code. So first you use the hash code to get to the bucket in your dictionary, and then you still need to do so the hash. So yeah, so right now, by the way, if you're really interested in the details, we actually do a hash code calculation of the entire thing for optimal bucketization and so on. And then once we also, when we do the equality check, then we have to do an equality check node for node recursively, going down all of those nodes. That we actually have to do. The hash code, we don't necessarily have to be exhaustive about. We might want to say, yeah, I'm going to just look at the top node or maybe one level beneath, and that gives us enough of a good, distribution of the hash code. We've not gone into this sort of optimization, but it's absolutely these are good questions, all of them. Sorry, do what? Sorry, out of this? Oh, a Merkle tree. Yes, I understand now. Sorry. Absolutely, we've definitely not gone into this level of optimizing of the cache. But these are all very good questions. That's not what EF Core does at this point. Right now, goes over the entire tree, gets a hash code, then does a complete equality of the entire tree. Okay. Very good idea. So basically what we've done to kind of move forward a little bit, we've introduced a new step here into this whole diagram is gonna get very complicated very soon. Like we're gonna be adding more and more blocks here. Yeah, I can see your eyes lighting up. Very cool. We're gonna see the architecture. So we now have a query cache. Very trivial. When the LINQ query tree comes in, we look at the cache. The first time it's empty, so we go do compilation. We get out our artifacts, our outputs. We store them back in the cache, obviously. And the second time that this thing runs, we jump over this and we have the SQL immediately. That's how EF Core is fast. That's really, really important. It means that here we don't have to worry too much about speed because it's only going to happen once startup per query. That's kind of the philosophy here. Everything clear up to now? This is all really just the introductory phase, to be completely honest. So now let's do a little thing. Remember our query here had a 3. So what I'm doing here is I'm going to extract it out. I'm just going to take it out. Okay? Very simple, right? So if you look at this purely with C# eyes, the code is exactly the same, right? All I did was extract it out to a variable. If you know a little bit more about C#, you know that we've actually done at the low level in the compiler, we've done something very, very different. Because we have a lambda here, and the lambda references a local, what do we call this in C#? A what? A captured variable, and the lambda has become a closure, exactly. So we've basically, this thing, for those not familiar with these concepts, the problem here is that we've handed a function to where. At the language level, we don't know when this function is going to get invoked. Maybe this where stores it somewhere else, and then at some point later, it's going to be invoking this code. We don't know when. Crucially, this code might get invoked after the whole method where we're in has already completed. It's already exited, and there's no more ID local variable because we've exited the function already. So what happens if this thing gets evaluated at that point, right? Because of this, all the languages that support closures, like most modern languages have some form of support for closures. When you have this thing where I'm referencing a local variable, this gets lifted up into an object on the heap usually, like this is what happens in C#, right? This ID, it looks like a local variable, but it's no longer a variable on the stack like a normal local variable. Instead, there's some sort of class that the compiler generates, and that class is going to have this ID as a member, as a field on it. And when I invoke the function that contains code, and a heap allocation is going to occur, and this closure is actually going to contain a reference to that heap object so that it can live even though the method that contains this whole thing has already exited. I hope you guys are kind of clear with this. This has nothing to do with EF Core. I'm just using this as an opportunity to talk about cool things in C#. But in EF Core, we actually use these C# captured variables or closures as a way of indicating that the thing here should become a SQL parameter. This is very, very interesting and arbitrary in a certain sense. So maybe you've noticed this in your EF Core programming. When you do this thing, your SQL will no longer have a 3 here. It will have a placeholder, like an @ID. Can anybody guess why we do this? Why are parameters important? Okay, that's a very good. I love that answer. SQL injection is all about, it's a security thing. It's about preventing. Sorry. That's the second. It's not about not polluting, but let me finish with the SQL injection. But that's also a very good response. So usually whenever you're inserting any sort of data like this 3 here into SQL, you have to be extremely careful because some user might put in, you guys know little Bobby tables, right? XKCD. If you don't know it, search for little Bobby tables right away. Like stop listening to me, take your phone out and look for that. That's a really funny comic that explains what SQL injection is. Basically, if you're going to be taking a SQL string and concatenating something inside of it, you have to make sure it's been sanitized. Otherwise, some user is going to terminate the string and then put something that drops your table from the database, and you're kind of screwed, right? But that's not why we do this. SQL injection is not a problem in this particular context, because as long as you're using EF Core with the LINQ APIs, EF Core guarantees that there's not going to be any sort of SQL injection. EF Core is the one building your SQL for you. You're not building SQL. And whenever it's going to integrate any sort of data into there, it is going to be sanitizing things for you. So if there's a single quote in there, it is going to escape it. There is no way to achieve SQL injection when using LINQ with EF Core. That's one of the nice reasons to use EF Core, by the way, is that you can be 100% sure that if you're whatever, you have to work extremely hard in order to allow for SQL injection. Like really, 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 really hard. You have to use special APIs that do concatenation into your SQL and so on. So that's not why we do this. The answer is more related to what this gentleman here said. And the reason is, so it's not exactly about pollution, but it is a little bit. The thing is, if you know a little bit about how databases work, when I send this SQL to SQL Server, I'm going to use SQL Server here as my example, but other databases work similarly. It's going to have to parse it, and it's going to have to plan how it actually runs the query. The planning process is actually quite heavy. You would be surprised. The database has to look now at the table here, and it has to look at this column, and it has to figure out, wait, maybe I have an index on this column, right? And if the query is very complicated, there might be several competing possible plans that the database is going to use based on what this query does, what indexes are available, and crucially, how much data there is in each table that is being involved into this query. So a database has some statistics. It knows that this table has around 1,000 rows, and that one has around 1,000,000 rows. And if you join those two tables, it's going to do it very differently based on how many rows you have in each table. Like, think about it a little bit. If you had to implement a relational database right now, there are typically three standard ways to implement a join in a relational database. And the reason you would choose one or the other is based on how many rows there are in each table that you're joining. So I'm trying to kind of say that this whole planning thing is complicated and long. And just like EF Core, like a really nice parallel for me, just like EF Core's compilation process is long, the planning process is long at the database, and the database also wants to cache that thing as well. So what the database is going to do in SQL Server specifically, this varies from database to database. When it sees a SQL, it's going to parse it, it's going to do the whole planning thing, and then it's going to cache it. And the next time it sees the exact same SQL, ASCII character by ASCII character, it's going to reuse the same plan and it's going to skip. There's a cache. There's another SQL cache, basically plan cache. So It's about pollution, but first of all, it's about reusing your plans. That's the first reason that we want to use parameterization. Because typically, of course, in this case, what you put in ID doesn't matter. The plan is going to be the same if it's 3 or 4 or 1 million, right? Like that's usually the case. So EF Core allows you to tell us this ID basically is, we're going to be executing the same LINQ query multiple times, but maybe this ID is going to have different values each time. That's basically the philosophy here. Therefore, this captured variable gets translated into a SQL parameter. Hopefully that's all clear for you guys, right? Yeah, that's basically the same thing. But this, of course, creates some issues with our caching story that we're starting to build out here, right? Maybe you guys are already seeing this. So if I look at the query expression tree with the captured variable, remember that here we had a constant, right? Where we had the 3. Now we have something else, if you look at this. What EF Core sees is actually a very nice low-level representation of the closure under the hood. Instead of having a constant with 3, we get a member expression. Like, this is super weird. There's no member here. There's no dot, right? If there's no dot, why is there a member expression? And what we have is a member expression over a constant expression referencing the closure object. Because a captured variable, in fact, is lifted to be a field on the compiler-generated closure object. If you ever look at these guys in ILSpy or some low-level thing, have you ever seen a display class with some special characters? Those are those guys, mostly. Okay, that's how it works under the hood. So what EF sees is really this kind of low-level under-the-hood reality. And the problem here, if we are looking at it from a caching perspective, is this. This is a constant expression to a heap-allocated closure object that will be different every single time we call this, right? Because every time we call into here, we're going to have a different closure instance with different IDs, obviously, with a different field value on it, which means that our cache will consistently always give us a miss. We'll always fail the equality check here because we have this thing that differs every single time. So how do we deal with this thing? Obviously, we want this to be cached, right? We still want to use the exact same SQL and the exact same kind of everything needs to be cached here. So let's extend this mechanism a little bit more. What we're going to do is we're going to introduce another step. I promised more boxes and things in the architecture. We're going to do another step here, which I'm going to call parameter extraction. We're going to go through the query tree before the caching phase, before the lookup phase. And wherever we identify this sort of construct here, this sort of parameter, we're going to extract it out and replace it with a custom expression tree that I've just made up. That's literally what it looks like inside EF, called query parameter expression. The actual value we're going to take out of the tree, it's no longer in the tree, we're going to store it in some other place where we shove the parameters. So now our tree has been kind of sanitized from, we've removed the parameters out, and what we've left is only a node that contains the name of the parameter, right? And by the way, here you can still make the argument that the name should not be relevant, a bit like the other parameter. That's a different kind of parameter, but anyway, we don't do that kind of optimization, at least not right now. So we've kind of, you can think about it as if we punched holes in the tree. Wherever we see a parameter, we kind of, we punch a hole in there, and we leave it kind of empty only with the name, so that we can now have a good caching story for it. It's a bit more interesting than this, but that's kind of like the level that we are right now. In 2 seconds, I'm going to say more. So we have now a PE phase here, the parameter extraction phase, which has to happen before the query cache, right? If it happened afterwards, then the whole thing would be defeated. That's the whole point. Everybody's still with me so far? Like we're still kind of not really where things are really hard. Sorry, questions? Oh no, I heard nulls. Nulls, exactly. So this is super weird. Why am I jumping to talk about nulls? What does this have to do with caching? You will see in a minute. So I'm going to do a big detour, but we're actually coming back to caching. Don't worry. This is really, and this, I always love talking about nulls when it comes to SQL. So clear your mind from this whole architecture thing. Now we're actually talking about something a little bit useful for you as database engineers and so on. Some people are covering their faces already because they maybe know what's coming. So I asked this question in many of my talks just for fun. So let's say you're EF Core and your job is to translate LINQ to SQL, and you have this link here. Give me all the customers whose first name is equal to the last name. So it's very obvious, like, let's just translate to where first name equals last name. obviously, if I'm asking this, then it's not that easy. Can somebody tell me in which case it's not going to work? Like in which case is this translation inaccurate? Correct, yeah, exactly. So when both of these are null, then C# will return those customers because null equals null in C#, but null does not equal null in SQL. And this is interesting enough. How many people know about three-value logic SQL and all that kind of stuff? Not that many hands, I know. So I'm going to spend one slide to talk about it, like really quickly. Because I think it's fascinating and not enough people know this. It's super interesting for me in terms of language design. So SQL is a different kind of language. It really is. It doesn't work like C# or your standard languages. C# is what we call a three-value logic language. In a normal two-value logic language like C#, a Boolean expression generally can have either true or false, as it can evaluate to true or false. But in SQL, something can evaluate to true, false, or null. You will understand this in just 1 second. Because of this kind of thing, so maybe I'll start with this first line, it's even better. When you approach the concept of null in SQL, very different from null in C#, despite the similar name, null in SQL means something like unknown or maybe missing data. I think missing data is even better. It's a database language after all, right? It's meant for querying data in your database. And you can think of nulls in the database as saying, the guy wasn't at home the day when we walked and asked what the first name and last name is. So we don't know it yet. We could maybe find it out tomorrow, but right now I don't know it. If you think about null in this way, the null equals null can't be true because we don't know what the first name and we don't know what the last name. So we can't say whether they're equal or not. They might be, but they might also not be because we don't know them yet. So the only possible answer to this expression is null. We don't know, right? The answer is missing. We don't have enough information to answer it. So this equality can actually have 3 different results, true, false, or null. And to drive this home, I've actually sat down and done the truth tables, if you guys remember your truth tables and so on. So a truth table for and for or in two-value logic is super simple, right? For and, you have true only when both of these are true and false otherwise. For or, things are kind of inversed. It's true everywhere except for the 2 falses, right? Very simple. Everybody knows this. Any programmer in the world knows this. So when we go to SQL or three-value logic, we have to add. Now we have 9 cells instead because there really are 3 things that are possible. And it's really, really interesting. If you do true and null, the answer is unknown because the answer depends on the value here, right? But if I do false and null, then the answer is false because we don't really care what the answer here is. We already know that the expression will evaluate to false, right? Because it's enough to have 1 false for the entire expression to be false, regardless of what this null is. Here you have the exact opposite kind of thing. It's null everywhere except where there's a true. So the moment there's a true on either side, we know the entire expression is going to evaluate to, right? Making sense? This kind of math? Yeah.
There is also an option in SQL, turn null on or off, I don't remember now the argument, at the connection level, and then this logic sometimes can behave differently. So
that's true, but this actually is the SQL standard. That is how so a specific database might have options and things, and you can make it work differently, but this really is very much by design. It's not some mistake or something made to confuse you guys, and it's actually very useful. Like, think about it for a second. Let's say you want to get all your customers who are above 60 years old to send them a gift. Okay, so you say where age is bigger than 60. Okay, you get a result set. Now you want all of those who are 60 and below. You want the other set because you want to send them another gift. I don't know, a card. So you do lesser than equal to 60, you get another result set. What about those who are null? What do you want to do with them? You want to send them this gift or that gift?
or twice.
Or maybe nothing, or maybe a third gift. It's a business question, exactly. But the point here is that your result set, your question splits your customers into 3 groups, not into 2 like in the normal world of C# or Java or Python or any other language. And that's a very important thing. Okay, everybody kind of got it? I think it's a really good idea for a data retrieval language. It makes a lot of sense for SQL. maybe less makes sense for C#, which is not a data retrieval language, but rather an imperative programming language. But for SQL, it actually makes a lot of sense. And from a language design point of view, I find this thing fascinating. However, given that we're EF and our job is to translate C# into SQL, that makes our job a whole lot harder. Because one of my jobs is actually to create a machine that translates expressions from 2-value logic into the exact same expressions in 3-value logic. Think about it. It's a bit of an academic way to explain what we do in EF. So to preserve the C# meaning of this C# code, we have to do a compensation and to add an or, first name is null and last name is null. And this compensation which EF adds is the thing that ensures that the semantics of these two things are the same. Does this make sense? Try it. Try it at home, by the way. Write a query like this, write this, and you will see this. And sometimes we get users saying, what the hell? What is this extra crap that I didn't write here in my query? And they're kind of angry at us. And we try to say, okay, your anger is understandable, but our contract that we have with our users is generally to try to preserve the C# meaning in the SQL that we generate. That's very important. And I have a very strong intuition that if we didn't do that, like if we just translate to first equals last name, then users, even much more users would complain, why don't I get the users where the two are null? Like, I'm pretty sure.
Okay, but if last name isn't null, like you add some kind of additional condition in the first one, the optimization will disappear?
In some cases, yes. But it depends. We're not great at this. We're not 100% great at this. For example, I know the part of the code where this sort of calculation happens. And for example, if you put it before, then it will work. But if you put it afterwards, it will not. Because we don't want to do too many passes on the tree. This is an optimization kind of problem, like really in a compiler. It's a difficult problem.
So the thing is to hint the optimizer and put hints up front.
Maybe. Like if you know your stuff a little bit and you're a really experienced EF programmer, then you know that if you do some things which shouldn't matter at all, like you just move the things around, suddenly your SQL becomes better. It's not great, and we have a lot of room for improvement here.
So always SQL profiler is...
Always. Like always with EF Core, always look at the SQLs for any query that you care, where you care about the performance. Most SQL queries, probably you don't care so much about the performance, and that's exactly why EF Core is there. But those where you do care about the performance, absolutely look at the SQL and does it make sense for you, and what can you do to make it better?
Okay, but this means that string nullability is not available at runtime, right? It's information about if string can be null or cannot be null.
You're talking about .NET nullability of references. Right. However, the important thing here is not the nullability in the C# in .NET types. It's what you tell us when you configure the model in EF. So when EF has a model, right? When you configure it, you say, here are my entity types and they're mapped to this and that. And you tell us, this is going to be required and this is not going to be required. That impacts the migrations that we generate. So when we do create table for you, we will say, based on what you told us, this is nullable, this is not nullable. But it also is going to impact this thing. And that's why this thing actually doesn't bother so many people. In many, many cases, like if one of these is not nullable, if you've told us that first name cannot be null, then we're not going to generate this stuff because we know, based on what you told us, that it's not needed. Except if you negate this. Like, I'm going to leave this as an exercise to the reader. Like, think about every time we think about this kind of stuff, if you put a not here instead of an equality, you'll see that things start to be very different. And the reason is, when you do where, the thing that comes after the where in SQL, if it evaluates to null, then that evaluates to false in the context of a where, right? So if you do where null, then that row is not going to come. If you so null is actually equal to false in that very specific context. But the moment you negate them, anyway, I don't want to spend the entire evening on these mathematical kind of logical problems, but that's the stuff I actually have to deal with. Once again, like this is the hard part of EF. Also, we just talked about equality, but there's all kinds of expressions in C#, and all of them have to be compensated for nullability, for null semantics, 2-value and 3-value logic. So what does all this have to do with caching and the query pipeline, right? Like, it looks completely unrelated to the rest of my talk. So let's bear with me just a tiny little bit. I'm still, before I get to that, I'm going to do the exact same exercise that I did before. Let's extract the name out and call it foo. Okay, here. So it's a captured variable again. So the naive kind of answer to how to translate this is this, right? We already know that this is incorrect, right? Because for the same reason, if name is null, then we're not going to get the correct results. What we actually need, I'm just following the same thing from the slide before. There's nothing new here. What we actually need to do is name is equal to this for the case where name is not null, or both of them are null. I'm doing the same thing. However, and this is important, in this specific case, we can do better. And the important thing is especially that adding this kind of stuff is a little bit too much in terms of perf. It's going to compromise too much the perf of this query, and it's basically going to not allow us to use an index efficiently. So we want to be able to do better, and we can. What we actually want to do for this case is to generate where name is null when we know that the parameter is actually null.
Because I got a question. The previous question, like name is null and ampersand name is null, returns just all customers. Because or and this returns true.
No, if name is not null and it's a specific value, like foo, then all those rows will not be returned.
If name is null,
if name is...
then it returns all customers.
No, because this is going to be null.
But or? Okay.
Then in the name is null. There is the part that checks the value.
Aha, name must be null. Okay.
Make sense?
Yeah, makes sense. Sorry.
This is not what we do in any case, but for perf reasons. It would be correct, but it would not be performant. What we actually want to do for the case where this parameter is null, we want to generate this because this would be the fast way in terms of database indexing. So this is now you're starting to maybe understand we cannot parameterize this. We cannot like put a single parameter in here, have one SQL that works efficiently, both for the case where the parameter is null and when it's not null. There is a construct in SQL called is not distinct from, but I'm not going to talk about it. I'm just mentioning it for completeness. That maybe allows this kind of thing. So what we actually want to do, now you're starting to understand why this complicates caching, is to have two different SQLs based on whether this parameter is null or not. When there's a non-null value, we want to do this SQL, which will be very efficient, assuming there's an index on name. And when it is null, then we want this SQL. That's amazing, right? That's exactly what you would expect EF to do. And that is what EF does, except that it means that we have one LINQ query and two different SQLs now. And for 5 parameters. How many different SQL permutations do we have? 2 to the power of 5, right? Yeah, that's not so good. But that's exactly what EF does. So I'm gonna let's introduce this into the query pipeline. Don't worry, we're gonna be okay. So I'm gonna make this a bit more complicated. This is a copy of what you saw before. I just made one small thing. What we have here is no longer the final SQL. We have an intermediate SQL in the form of an expression tree. This is no longer a string, something I can send to the database because we're going to be doing more stuff with it now. Up to now, very, very important, all of this stuff does not have any access to any of the parameter values. That's very, very important. Like in terms of how we design the code here, there's literally no way we don't expose any reference to the area where we have actual values. If we did, and somebody made a mistake and looked at the parameter somewhere in here, then the result would differ based on parameter values. And that would be chaos. That would be a bug, a huge bug in EF core. Everybody's clear on this, I hope, right? Like we have to put a blindfold in front of our eyes as we're compiling. We cannot know any sort of parameter value. But once we've gone past this point, we have a second cache. We have a multi-layer caching system inside the EF core pipeline. This is the SQL cache that's mainly there to deal with the problem that I just told you about, the nullability of parameters. It's really mainly there for this one problem, which is a very important problem. Here we do some additional processing, specifically around getting the final SQL to put the is null or the equal parameter that you saw just in the slide before. And we're going to cache this thing again so that we don't have to do this additional processing every single time. This is like one of the more complicated parts of this talk, I think. So the cache key of this, so remember, we get here, remember the query that we're looking at, right? We're comparing the name to some parameter, and that parameter can be sometimes null, sometimes not null. So we're going to have a cache key that is the combination of the nullness of all the parameters that are in the query. If we have just one parameter in the query, then we're going to check, is that parameter null? If so, then we have one final string, and if not, then we have another final string. The second time we go around compiling this query, if we see that we've already had a query where p was null, we can jump over this additional processing and we have the final string. And it's true that if you have 5 parameters in here, this cache will have 2 to the power of 5 permutations, and it also has an upper bound on the number of sequels that it has. Making sense still? This is hard, right? This is like already starting to be a bit weird. This is a place where SQL and the fact that it works this way around nulls we don't have any other choice. If we want to stay performant, we have to have this additional phase here, unfortunately. Yeah.
Since we took this approach right now that we have access to the parameters now, does
Yeah.
the first query where we parameterized the expression where we had the query parameter?
This part,
Yes.
the PE.
Yes, exactly. Do we now have in this second cache all the permutations of these different parameters that we had, or do we still keep the previous version where we have just this parameter that's kept in the heap and we only access it from the heap?
I don't know if you guys are still alive for one final section afterwards. We'll vote, because that's a little bit what I'm going to be talking about. But the main thing that we do here up to now in this talk, what we do here is we don't look at the parameter values, because still we don't want to be able to look at the parameter values here, because that would defeat, again, the caching. But what we can do here is to look at the nullness of the parameters, because that's part of the cache key that we have here. So there's a very specific API that the code here can call to check, is this parameter null or not? It can't actually access the value. It can, but then it triggers something else. Make sense? Answer your question?
Yes.
Good. Any other question here? Are you still okay for 10 more minutes? Yeah, I'm seeing nodding. Okay, good. I promise I'm gonna try to not like talk too much, but this is the last part, and it's the last complexification of this whole story. Once again, I'm going to go to a completely unrelated thing, like we talked about nulls. Now I'm going to talk about a thing called parameters collections, and then we'll go back into our caching story. So let's do this exercise again. We've got the contains. Contains is another LINQ thing where we can do where new123 contains BID. This is basically a way to get all the blogs where the ID is one of several values. So I know it's 1, 2, or 3, and now I want to get all the customers or blogs where that is the ID. Everybody's familiar with this stuff, right? Like this is very basic LINQ. Fortunately, in SQL, we have a really nice construct for this, nicer than in C#. This is one of those cases. We've got an in operator where I can just do 1, 2, 3. This is something that I'm kind of missing in, by the way, in C#. We don't have an operator like this. Like this is somewhat ugly in my, like today we can use sometimes collection initializers and so on. Anyway, it doesn't really matter. This translation is really straightforward, and it actually also works. There's no trick here. This is actually a correct translation semantically, and we don't have to do any problems here. So that's very cool. But once again, I'm going to do, it's already the third time in this trick, in this talk that I'm doing this trick. I'm going to lift out this thing to a variable outside, to a local variable. Third time already, because it causes trouble every single time. So how do we translate this kind of thing? Does anybody have an idea or a suggestion? Like I can't take this thing and replace it with a parameter. Anybody who knows SQL knows that I can't put a parameter here instead of the in. Yeah.
I'm not really sure, but we are like translated to JSON, and then
You've been reading you've been following a little bit on what EF has been doing in the last major versions, right? That's good. No, it's cool. I'm asking also to understand if people are aware of like what we're working on and doing. So
I think in Postgres you have things like a nest, so you could probably also parameterize.
That's a very good, though we don't actually need a nest for this. Even in Postgres, we can do something even simpler, but that's a very good comment. And we do a nest in some other situations. I'll talk about this in a second. Sorry?
We can have a bunch of ors.
We can have a bunch of ors.
It doesn't scale like...
What would be the problem with bunch of ors? One of the...
We have 10,000 of IDs, then it's...
Right, and the SQL changes every time we add an OR. So then again, we defeat the SQL caching at the database as usual, right? TVPs, table valued parameters, like yeah, that's a SQL Server only feature, more or less, right? Which is already a problem for us. It also has its problems. You have to define the type in advance, which we can't. We can't define types like this. This is just a query that we see. We can't. Basically, it's unusable for us, unfortunately. Lots of great suggestions, really. I'm not just saying this like, actually, they're really good suggestions, and we went through them, kind of like discussing all of them. So the main thing is that most relational databases, this is the general, don't have array types. If only we had like a first-class idea of an array, then we could indeed just send a parameter here somehow that would represent the array. And that's what we do in Postgres. Postgres has an operator called any. It's very special. You can do where something equals any, and then you put an array. And the array is an actual type in the type system of Postgres. It's the only database, as far as I know. I think Oracle has a thing. No other database has like a serious type, like full-blown kind of array type system, because relational databases are all about scalars and unordered row sets, right? Like they're all about sets and scalars, and there's no such thing as, and this is why whenever you do need to have a bunch of tags in a database, right, on your blog, you have two options. Either you have another table and with rows and a foreign key relationship, and then you have to join in order to just get the, to get the tags, which is a pretty expensive and heavy operation. Or you go the simple route and you concatenate them into a string with commas, which is the shitty kind of route, but it is the efficient thing that you do. You kind of denormalize it and make it into a shitty thing, right?
Query over XML, like in SQL.
Right. Right. So, and that's where we start to connect to the comment of the gentleman in the back. XML is not so much in vogue, thank God, anymore. Thank God. Like I went through the whole XML phase as a developer, and it was not necessarily very pleasant. Today, obviously the thing that kind of won the war is JSON, and everything. We at some point we got the NoSQL databases, and the NoSQL databases like Mongo and the Cosmos and so on are all about, instead of having tables and relationships between them and joins, you've got a nested hierarchical table that's kind of, you can think about it as a JSON document. That's basically what it is. And because NoSQL was really working very well and it solved actual problems, like the one that I just said, like putting those tags, all of the relational databases also started doing the same thing. And today, basically all of the major relational databases, you have got good JSON support, and EF actually leverages that. Okay, so Postgres has arrays as well, and that's amazing, but it also has first-class support for querying JSON efficiently and everything. SQL Server 2025, which just came out very recently, now has a JSON type and full-fledged querying capabilities as well. Like this is the world in 2025. It was the world already a few years ago, in fact, but anyway. And the reason I love this is that it gives me an opportunity to talk about a big fail that I personally did as a sort of an architect inside EF Core. We don't usually hear about people's big fails, so this is one of those opportunities, and I actually like to talk about it. So now I'm going to answer the question that I asked the crowd. Before 8, what we did with this query was something that we knew was not great. Everybody knew it was not great. What we did was we inlined this array into the SQL as constants. So we just shoved it into the SQL, and that's it. That actually performs kind of okay in terms of like the SQL works, but of course it means that every time I change anything in this parameter, it's going to produce different SQL. Therefore, it's going to be replanned. And here we really get to what you said before. The problem is not even that we're going to replan. It's that if these things change all the time, then we're going to be constantly inserting new SQLs into the cache inside SQL Server. So the cache inside SQL Server is going to grow and grow. And we're going to end up evicting legitimate SQLs that we want to keep in the cache. But this technique that we did here kind of pushes them out. So this is actually really quite bad for performance. And for a very long time, this was the most highly voted issue in the EF Core repo, which is saying a lot. We have a lot of issues and a lot of engaged people. And the one at the top was, please fix this. Don't do this anymore, because perf-wise, it's not great. And it's a hard problem for any ORM. Anybody doing SQL knows that this is a very hard problem. There's actually no real solution to this problem. So what we did, as we've just been discussing, I became, with EF Core 8, we arrived at the decision, now is the time to do JSON and to do it right and to do it nicely. And we also thought that this would be the right solution for this translation problem. So in EF Core 8, you see this thing here. What we do is the in, instead of having the values here, has a subquery. And the subquery, this is SQL Server, has this OpenJSON function, which gets the as a parameter. This is just a string. We basically took this array and packed it as a JSON string here. If you look at it, it's literally a string that has brackets and inside it 1, 2, 3. So it's a JSON string, one string. Because it's a string, we can send it as a parameter. It's not an array anymore. And then OpenJSON is a cool function that takes a string, parses it inside SQL Server, and exposes the result as a result set, as a table. It's basically a table. It's very similar to a temporary table conceptually, not technically. Conceptually, it's a bit like a temporary table that gets constructed out of a JSON string, of a JSON array. And okay, so it actually in most cases is very, very good also in terms of performance. So the actual parsing of the JSON is not so bad. That's not the problem. And we, of course, profiled this, benchmarked this, and it was actually working very well. But it does have one crucial problem with performance. The planner, when it looks at this query, has no idea how many elements there are in this parameter. Because this is a string. It's not actually an array, right? And we already said that, so this is a parameter of a different type from the other parameters that we've had. Before we had just a single int. It doesn't matter. The planner doesn't need to know anything about it. But with this parameter, which is conceptually an array, that could actually have an impact of, once again, is this OpenJSON going to be huge or is it going to be small? That's going to be very, very important for knowing how to join it or to look for stuff in it in terms of planning. So what we did with this translation was to deprive the planner of the database query from some very important information, which is how many rows there are in this thing, in this collection. And indeed, once we did this, we started getting some reports of, in most cases, it was working fine. In many cases, it solved completely, by the way, the problem of query cache pollution, because now the beautiful thing about this is that it's just one SQL. So you get one entry in the SQL cache in the database. It's amazing. It solved the problem that it was supposed to solve. It was performing well in most cases, but in some cases, queries that took nothing, like 2 milliseconds, suddenly started taking 5 seconds. Like we had a huge performance cliff in some cases, unfortunately. And we dug into this, and the problem was that the planner can no longer know and chooses a very bad plan that doesn't fit the number of rows in this table. Make sense? All right. We finally fixed this in EF10, which came out only a couple months ago, or 3 months ago. This now aligns with Dapper, for example, does the same thing, and some other industry standard. This is a more classical solution to the problem. I personally thought I had like the cool new thing, and I was excited with JSON, and I made a mistake. It was the wrong solution. So what we do in EF10 by default is we now inline it, but with parameter placeholders. That means that the values can change, and the SQL stays the same, but number of values cannot exactly change, right? For the problem of changing number of elements, what we call cardinality, we even pad or bucketize. So if you actually look at this query, you'll see 5 parameters, even though there's only 3 here, because we have buckets. And then what we do is we're going to duplicate. 4 and 5 are going to have the same value as 3, just so that we have less number of SQLs to cache in the SQL cache.
So one question, if you get something like maybe powers of 2 in the end, use union all, is it more, did you try it maybe if this is like more performant, then for example you can just combine maybe 3 parameters with 8, or sorry, 3 is
you're talking about the bucketization strategy. Yeah. Like here, we did do some cursory investigation, and we also we took a lot of inspiration from the Dapper algorithm for bucketization. I'm sure there's more to do there, like in terms of what is the optimal bucketization. It's also this kind of problem where there's no correct solution ever. It's all like, this is this sort of problem where it's sometimes going to be better here, sometimes there. Because of this, by the way, very important, in 10 specifically, we also have a lot of knobs. So there's now 3 modes. You can actually tell us exactly what you want. This is the default, but you can ask for constants, the pre-8 behavior, or you can ask for the OpenJSON solution. All of that is still there, and it's up to you to choose it.
On what level do you configure that?
Sorry?
On what level do you configure that?
2 levels, either globally what the default is, or overriding on a specific query. So we really went all out because this is the problem where there is no correct solution. We gave up and we said, okay, we'll choose the reasonable default, but we allow you to configure it both at the default and at a per query level. So it's really up to you to now, if you know your stuff and you look into your SQL and you really want to go into this, at least have the EF mechanisms for telling us exactly what you want.
So, for example, can you have the JSON thing with hint optimized for? And
You mean the SQL Server query hints? Yeah, that's a different question, and we don't currently support query hints with SQL Server, but you can still add them as SQL with an interceptor. Like you can still kind of shove in, if you want to just shove a query hint into the query, you can do this.
Yeah, but then I guess it would be difficult to do it in every single database.
I mean, hints don't even exist in the same way. Like it's a completely different, the concept of hints is like very database specific. That's one reason why we haven't done it up to now. But in general, you should not need to, the guidance is in general, you should absolutely avoid using hints until you really, really have to. That's basically the guidance. So I don't want to keep this for too long. I want to start getting to the end of this. Now, again, remember that we're talking here about caching. So what is the relevance of all this to the caching? Remember that now we have this weird situation where the SQL starts to vary not based on the nullness of the parameters, like we said before for the nulls. Suddenly it also starts varying based on the cardinality of the array, right? Like if the array is bigger, then suddenly the SQL is bigger. So we're again breaking our caching mechanism by doing this. Now, we could like make a caching mechanism that works with array cardinality and all that. We didn't do that, at least not yet. What we instead did was that if in this part of the query pipeline, we decide that we want to do something else, like that goes beyond just looking at the nullness, then we have an option of disabling SQL caching, and at that point, it's legal to look at the parameters and to do whatever we want. So we basically did an escape hatch. And at this point, we can basically here, whenever we see this sort of parameterized collection, we say, okay, let's stop. We're going to disable the cache. Whatever comes out of this thing, it's not going to get cached. It's a one-off thing. And then we look at the array parameter. We see that it has 10 parameters. We engineer whatever SQL we want. It doesn't matter because we're not going to cache it. And we send it to the database. It's kind of like this sort of trapdoor that we can use. The nice thing about it is that this is actually quite light. This doesn't take a lot of work. The work is here, and this still gets cached. That's our first layer cache and not our second layer cache. So doing this again and again for each query is frankly kind of negligible in the grand scheme of things, which is why it's kind of okay. It's not perfect, and maybe in the future we'll evolve this caching mechanism to also allow us to do this sort of fancy thing and also cache. Like have one SQL as long as the parameters are up to 5, and another one as long based on the bucketization, right? That would be like that feature maybe, but that's a bit too much. All right, this is actually what it looks like. Done. That's actually like the schematic overview of the query pipeline in terms of caching. There's two levels of caching here. One at the very start of the query after we've done the parameter expression. Another one for the SQL caching where the key is parameter nullness because SQL is so weird around null. So we don't have a choice. There's also a facility for disabling SQL caching altogether when we want to do something completely crazy like we have to do with parameterized queries. So this gives you an idea of the sort of complexity we deal with in EF Core. And now we go to my last slides. All of this stuff, all of it almost, is a problem because we translate LINQ to SQL. Most other ORMs, like an ORM like Juke, doesn't have to deal with this in general because they don't need to care. The user just expresses SQL directly. So a Juke user has to think about whether they want to use OpenJSON or choose the strategy that they want for parameterized collections themselves. They have to know SQL. They have to know about the three-value logic problem and engineer the null stuff themselves. If they want to compensate and have null equals to null, they have to write out that stuff themselves. So all these other ORMs are much more low level. You have to actually be, at a position where you understand all that stuff and you write it out. Whereas we go much more high level. We tell you, you're just going to express yourself in C#, and we do all the heavy lifting of taking that and doing all this weird crap that you just saw to make it behave the same way and also be efficient, which I hope kind of drives home the point of why EF is really a crazy kind of product. It's not the average sort of ORM if you kind of compare it. And I've heard a lot of people, when you go from .NET whatever other kind of language. One of the things that you don't find there is an ORM like EF, because nothing like this exists in other languages as far as I know. So yeah, you have to be kind of, there's a trade-off here. EF core is extremely complex. That's why it's still, let's say, you need a lot of investment into it. Even after 10 years now, we're at EF10 and we still have a lot of stuff that we still haven't done. And I'd love us to do, but it's because it's that complicated. And be nice to your neighborhood ORM developer, because we're doing a tough job, as I hope you guys saw. That's it. That's the end. And I hope I didn't take